Relative motion is how things move, or the study of how things move, relative to one another. So if I want to talk about things moving relative to one another, a really good example is a river. So this is a river. And this river flows south. I'm going to draw an arrow here to show the flow rate of the water. And I'm going to label that arrow. I'm going to call it the velocity of water dot shore. And what that means, the code here is velocity of water relative to the shore. The dot means relative to in this context, okay? In the subscript, we've got water dot shore. That means velocity of water relative to shore. And the short form that I'm going to write, because I'm not going to write out that enormous subscript every single time, is velocity of W dot S, water shore. And so anytime you do a problem involving river or moving water, we're going to just accept that W dot S is water relative to shore. Because shore is like a nice thing to measure the flow rate of water with respect to. And I'm going to use the word with respect to. Okay? Water with respect to the shore. Something that might be on the water could be a boat. And this boat's pointing south, according to our reference frame. And we're going to say that this boat could have a velocity of boat. Now, we're going to talk about the velocity of the boat relative to the water. So velocity of B dot W, boat relative to the water. And the reason we're going to say boat relative to the water is because we could have a boat on still water, right? Like on a pond. So we typically talk about a boat's ability to move with a certain speed with respect to the water on which it sits. And if the water happens to also be moving, that's great. And people say, if I want to find the velocity of an object relative to something stationary, I have to think about it as the velocity of that object, and I'll just short form that as OBJ, with respect to the medium in which it finds itself, plus the velocity of the medium, I'll just short form it as med, with respect to some stationary reference frame. Some stationary object, stat, stationary. And I could shorten this up just to make it a little bit less cumbersome with the subscripts. I could write it as VOS equals VOM plus VMS. Yeah?
How did you get that?
Well, let's think it through. It's really just logic. I'm not making it up like sort of magically or anything like that. I'm just trying to say, hey, look, if I was on let's say a cruise liner, and I wanted to know as the cruise liner passes an island, say maybe in the Bahamas, on one of these nice little cruises, right? People do that all the time. And I'd like to know, for some reason, what my velocity is relative to the palm tree on the beautiful little island. Say I want to do that. Okay, maybe that's important to me for some reason. I could do it. But what I'd have to think about is not just my velocity as I walk on the boat, it would be the velocity of me, plus the velocity of the medium or the thing that I find myself on, or sorry, my velocity of me with respect to the thing I find myself on, plus the velocity of the thing that I find myself on with respect to the coconut tree or the palm tree. Okay, so I have to think of it as sort of a vector sum. And since we talked about resultants last day, it only seems fitting that we talk about this today. Okay? So in the case of the river, the object could be the boat, and the stationary thing could be the shore. And the way I'd get the velocity of the boat relative to the shore, the object relative to the stationary thing, the shore, would be to figure out the velocity of the object relative to the medium. In this case, that's the water. So how fast a boat can travel in still water, plus the velocity of the medium, in this case the water, relative to the stationary thing, which is the shore. It's kind of like that old song. The the cat was in the tree, and the tree was in the hole, and the green grass grew all around, and the green grass grew all around. You know that elementary school song that you sing? There's like this chain of things, one within another within another. Well, this is an object in a medium, and a medium within the world. And we're sort of looking at the motion with respect to different things as we move our way down this chain. And one thing I want you to notice is that this medium and this medium kind of butt up against each other in the subscripts. It's like they're joiners. And so keeping that idea in mind, I want to think about the velocity of the boat and the water, and the velocity in the water of the water and the shore. I'm going to attach some numerical values to these. I'd like to say that the velocity of the boat with respect to the water, like if the water was stationary, would be 5.0 meters per second. We've got a motorboat, let's just say, and it can go at 5 meters per second. And for this particular river, I'd like to make the claim, you know, I've sat there, I've figured out the flow rate of the river. It's got a velocity of 10.0 meters per second south, as indicated in the diagram. 10 meters per second south. And if I wanted to figure out velocity of the object relative to the stationary reference frame, that would be velocity of the boat relative to the shore in this case, because that's the stationary reference frame, is equal to the velocity of the boat relative to the water. Notice that's the object relative to the medium, plus the velocity of the water relative to the shore. And again, that's the medium relative to the stationary reference frame, the shore. And what I know, well, you could probably tell me this through common sense, although there's nothing really common about sense anymore, it seems. What would be the velocity of the boat relative to the shore if the boat were to point itself downstream and just drive at 5 meters per second relative to the water? What would the velocity of the boat relative to the shore be? Yeah.
15 meters per second?
Yeah, 15 meters per second south. That's what some sensible people would say. And if I follow my logic that I've said here, we should get to the same conclusion, because if your sense is sensible, and if this reasoning is sound, they should agree with each other, right? So the velocity of the boat relative to the water, 5 meters per second. South. We should call south positive, since all this stuff is happening south. And let's call north negative this time, because that makes sense in this context. And velocity of the water relative to the shore, also south, so it's plus 10.0 meters per second. And as the man says, the velocity of the boat relative to the shore, or the object relative to the stationary reference frame, is going to be 15.0 meters per second, or 15.0 meters per second south, since it's a positive result. Yes, ma'am?
So, velocity of water to shore, that's one whole thing?
Yeah.
Okay.
Yeah, it's just one expression, one value. So here's what I want to propose. Here's the what if. What if, and I'll draw my what if in green. My what if is, what if my velocity of the boat relative to the water changed direction? In other words, what if I pointed my boat upstream and tried to battle the stream? You tell me with your common sense, what would the resultant velocity be? And then we'll tackle it using the systematic approach. And of course, we're using the systematic approach because the situations get more difficult than this. But if we can navigate the simple, then perhaps we can navigate the complicated. Yes, sir?
Would it be 5 meters per second? Or,
Yep.
yeah.
What direction?
South.
South. It would be south. Yeah, it would be south. So this is what we said once before, and I want to point out that we're going to say the same thing again, or at least that's the way it's going to start off. Oh, I should have put vector signs over these. We're going to make the same statement again, that the velocity of the boat relative to the shore, it only makes sense, is going to be the result of the velocity of the boat relative to the water plus the velocity of the water relative to the shore. It only makes sense, right? How fast I go relative to the thing I find myself in, plus how fast the thing I find myself in is moving relative to the rest of the world, is going to be how fast I move with respect to the rest of the world. That's the story, okay? But this time, when I plug in my values, velocity of boat relative to the water, is it going to be positive or negative 5 meters per second if I point myself upstream? Yeah? Negative, yeah. Negative, I wouldn't have asked if it wasn't something different, right? 5.0 meters per second negative plus 10.0 meters per second is equal to 5.0 meters per second. Or in other words, I'm going to get washed downstream at a rate of 5 meters per second if I try to point myself against the current, which you told me using your common understanding of the way the world works, but here we got it in a systematic approach, okay? So it's always nice to systematize what some people like to call common sense, recognizing that some people have none. Yeah?
Do you have to write a vector like saying which direction it goes?
Oh, yeah, we could add that on to the end. Yeah, we could say that that's south. This might be of particular interest to somebody if what was at the end of this river was a waterfall. Right? I mean, that somebody might care about that sort of thing. That's a calculation that you might be doing in your head. Oh my goodness, it's 10 meters per second flow rate and I can only do 5. What am I going to do? You better turn sideways or something, honey. Or else you're going to go over this waterfall if you don't. Make sense? So, somebody might care about this sort of thing. It might be particularly interesting to someone. Here, yeah, to the calculators. All right. So I could call this part A. I could call this part B, given our little scenario. But a part C that might talk to this story would be this what if. I'd like to throw a third what if out there. And I'm going to use a blue marker, and maybe it shows up as blue on your screen, maybe it doesn't. But that is blue. This little arrow here, that's going to be the velocity that I would like to take now with respect to the water. So my current velocity of the boat with respect to the water is 5 meters per second, but I'd like it to be west. So here's how I want to write this down. I want to write C, velocity of boat relative to water is going to look like this. The velocity of the water relative to the shore is going to look like this. And what I would like to figure out is the velocity of the boat relative to the shore. So as we said before, you can write it out. Notice that the equation isn't changing. This with respect to stuff doesn't change from time to time. Velocity of the boat with respect to the shore is still equal to the velocity of the boat with respect to the water, object with respect to the medium, plus the velocity of the water with respect to the shore. And I can plug in my values, except for this. Can I just add up 5 and 10 this time? No. How many dimensions am I dealing with now? 2. Now it's not a one-dimensional scenario anymore, right? So I've got to deal with this graphically now, or with vectors, I should say. I really need to draw the vectors this time. And whenever I draw vectors that add up like this, I've got a W here that is the joiner. That indicates that those guys can get added up nicely, tip to tail. That W is a nice indicator to me that these guys are going to add up tip to tail. And so I can do VBW, I'll draw it, I'll do it in blue. VBW added tip to tail with VWS, there's that W being almost like a Lego piece joiner between these two vectors, joining them up. What's the resultant going to look like? Just one second. What's going to be the resultant motion of my boat? Is it going to go straight west? Yeah. Yeah, kind of on a diagonal, sort of like southwest, right? Southwest isn't a good word. Southwest means south 45 degrees west. So sort of in that quadrant though, right? We're going to kind of go down like this. It's going to kind of look like that. And so if I want to find out the resultant velocity, I'm going to have to find a direction, and I'm going to have to find a magnitude, because velocity is a vector after all. Velocity of the boat relative to the shore. So there's 2 things I'm going to have to do here. I'm going to have to do some SOHCAHTOA, good old-fashioned SOHCAHTOA, and I'm going to have to do some Pythagorean theorem. I want to know a hypotenuse. I know 2 values, and I know 2 values that are the opposite and the adjacent, and I know a theta value. That means I'm going to be doing an inverse tan function, and I'm going to be doing a Pythagorean theorem calculation. Now I'm going to write down the calculations. If you want to not look, avert your eyes and try it on your own, that's fine. Or if you want to just copy down what I write down, that's okay too this time, okay? So I'm going to find the angle first. Tan theta is equal to the opposite VWS over the adjacent VBW, or theta is equal to tan inverse of VWS over VBW is just going to be my 10 over 5. Meters per second over 5 meters per second. Or in the end, I should get about 63 degrees. That deals with the angle. Now I want to deal with the magnitude. The magnitude's a Pythagorean theorem calculation, so I can say VBS is equal to the square root of, that's just taking that square over to the other side prematurely maybe, but no, it'll be okay. Square root of VBW squared plus VWS squared. And if I square 5, it'll get me 25. And if I square 10, it'll get me 100. So I'll have the square root of 25 on my hands here. Square root of 125 meters squared per second squared. And my math form's going to be a little bit off because I've run out of space, but the square root of 125 should be about 11.18 meters per second.
You should put page, please.
Yeah, sure.
Just the-
Want me to shift it up a little bit?
No, it's on the side.
Okay. I know, Mike. There we go. Contrast is back again.
Can I ask my question?
Hold on. We're almost there. Okay? And then I promise. I'm not trying to shortchange it. All right. The final velocity then, once I've got my magnitude and my direction, would be V with an arrow over top, BS, velocity of the boat relative to the shore. And yes, I know I'm saying BS over and over again, but it's not. It's all true.
Makes sense.
Okay? 11 point, and I should take it to 2 significant digits because I started off with 2 significant digits. So 11 meters per second. And now I might say west, 63 degrees south. Oops, south. But then some textbooks and some people might not like that because 63 is bigger than 45. So you could also say, more correctly maybe, south 27 degrees to the west. And I prefer that a little bit. Okay? And then there's still some other people that might say 27 degrees west of south. And if you like that better, that's okay. Feel good about physics. Physics is all about feelings.